Welcome everyone, and welcome to another episode of Bird Math. Thanks for watching. Today, we're going to be talking about the mean value theorem. This is a very common topic in any calculus class, so if you're taking calculus now or you've taken it in the past, you're probably familiar with this. Or maybe you just want to learn about it and you want to learn math for fun. Either way, hopefully this video will be helpful to you. So let's talk about the mean value theorem, and let's start with the definition. If I have some function f, and this function is continuous on the closed interval from a to b, and the function is differentiable on the open interval from a to b, then I can state the following. There must exist a c in the open interval from a to b such that f prime of c is equal to f of b minus f of a over b minus a. So that's the definition. And let's walk through this slowly to see what exactly this means. So here you'll see I have a function f. And from looking at this, you can see that the function is continuous from x equals a to x equals b. If you're not sure exactly what continuity means, a quick and dirty way to think about it is, can you draw the function from a to b without picking up your pencil once? And here you can see you clearly can. There's no holes, there's no asymptotes. It's a nice continuous function from a to b. Also, is the function differentiable on the open interval from a to b? So we don't necessarily care about exactly x equals a and x equals b, but on the open interval from a to b, is the function differentiable? And if the function is continuous from a to b, and there's no kinks, like something like you would have in an absolute value function, which we don't see here, then the function is differentiable. So the first two requirements of the mean value theorem are satisfied with this function f. It's continuous and differentiable from x equals a to x equals b. And so if that's the case, then I know that I can state the following, and that is f prime of c is equal to f of b minus f of a over b minus a. And what that means is, you'll notice here that this is just a formula for slope, this part right here. So if I drew a line connecting the points a, f of a, and b, f of b, like so, well, this is a straight line, and this has a particular slope. To find the slope, you would just use the slope formula. I have 2 points, a, f of a, and b, f of b. And this is the formula for the slope of that line. We typically call that a secant line. So what the mean value theorem then says is that because the first two conditions are met, there has to exist a c somewhere in between a and b, such that the slope of the tangent line at that point on the function is equal to the slope of this green secant line. So if I can find somewhere on this function f where a tangent line would have the same slope as the secant line connecting a, f of a, and b, f of b, well, I know it must exist, and I know that that point must be between a and b. So it looks like to me that it's going to exist about right here. And there we go. That has the same slope as the green line. And the c looks to be about right there. So I know that that c must exist somewhere between a and b. That's all the mean value theorem is saying. So we're going to go through a couple examples here now, and hopefully this will help cement the concept. So here's an example. We have a function f of x equals 1 over x. And I just want to show that the mean value theorem applies to the interval, the closed interval 1, 3. Okay, so we look up here. First condition, is f continuous on the closed interval? In this case, from 1 to 3. And number 2, is f differentiable on the open interval? In this case, 1 to 3. Well, certainly seems that way. It's certainly continuous from 1 to 3. And there's no kinks or anything like that, so it's definitely differentiable as well. So therefore, I know that the mean value theorem does apply. And I also know that if I drew a secant line connecting the two endpoints of the interval, so I'll just mark them here. This point right here is 1, comma, f of 1. And f of 1, the function is 1 over x, is just 1. And this point here, well, 3, f of 3. Well, f of 3 is just 3 plugged into f, so that's 1/3. If I drew a secant line connecting these 2 points, there we go. So that's my secant line, my green secant line. And I'm going to find the slope of this secant line. So let's do that. So the slope of this line, we'll call m, is f of 3 minus f of 1 over 3 minus 1. Well, f of 3 we know is 1/3. And f of 1 is, we know, is 1 over 3 minus 1, which is 2. So m is equal to 1/3 minus 1 is negative 2/3. And then divided by 2 over 1, or multiplied by 1 over 2, we get negative 2 over 6, which is equal to negative 1/3. So the slope of this line, this green secant line connecting the two endpoints, I know is negative 1/3. So because the mean value theorem applies here, which we just shown, because f is differentiable and continuous on the interval from 1 to 3, then I know that there must exist, and that's what this little sign here means, by the way. This just means there exists. And if you ever take any higher level mathematics, proof-based courses, you'll definitely use that. So there exists a C in the interval from 1 to 3 such that f prime of C is equal to the slope of the secant line connecting the two endpoints, which we just found out, and we just found out it's negative 1/3. So there has to exist a C where if I drew a tangent line, the derivative at that point is negative 1/3. So let's do this graphically first, and then we'll actually find the actual value and see if we get close. This, I'm not the best drawer of functions, so it might not work out exactly, but let's see. So this looks like if I drew a tangent line on the function in between the interval from 1 to 3, because I know the C must exist between 1 and 3, it looks to be maybe about right there. Yeah. So let's draw that line. Okay. So it looks like it's going to be around x equals 2. about. And that makes sense. 2 is between 1 and 3. So let's find the actual value now. Because we know f prime of c. Let's find this actual c value. Because f prime of c must equal negative 1/3. So the first step is let's find the derivative of the function 1 over x. And we know that that's negative 1 over x squared. And I should probably just show that work really quick if you guys are wondering how I figured that out. So remember, our original function f of x is 1 over x, which I can write using negative exponents as x to the negative first power. So therefore, f prime of x, just using simple power rule, is negative x subtract 1 to negative second, which is equal to negative 1 over x squared. Okay, so I know that there must exist a c. Let's erase this for a second. Such that f prime of c is equal to negative 1/3. Well, there's my derivative function, has to equal negative 1/3 at one point. And let's solve for x. So we'll multiply both sides by x squared, and we'll get negative 1 equals divide both sides by negative 1/3. That will give me positive 3. So x is equal to the square root of 3. And is the square root of 3 on the interval from 1 to 3? Absolutely. Absolutely. So we just proved, and by the way, this square root of 3 is our c. Okay? So we just showed that the mean value theorem applies to this function. We showed there had to exist a c between 1 and 3 such that the slope of the tangent line at that point c was equal to the slope of the secant line, the green, connecting the points 1, 1 and 3, 1/3. All right, and let's go to a final example here. And this is more of an application of why is this, theorem useful? Well, here we have a position function. And a position function is typically denoted s of t, where t, the independent variable, is t, which is time, and the dependent variable is distance. So this function will tell you how much distance that you traveled, depending on what you input, how much time that you input into it. So if I take s of 1, in this case hours, this function should tell us how much distance was traveled after 1 hour. And if you don't know, the derivative of a position function like s of t, s prime of t, is velocity. So let's prove that the mean value theorem exists, and we're going to see this particular interpretation of what that means here. So we know that in this case here, this object or this particle or point or whatever traveled 180 kilometers after 2 hours. You'll see here, okay, on the x-axis is the t-axis is 2 hours. At time t equals 2 hours, we traveled 180 kilometers. And we started at 0 kilometers at t equals 0. So the average velocity over these 2 hours is simply connecting the 2 points, the starting and ending point, and taking their slope. That will give you average velocity over the whole 2 hours. So let's do that here. And we can see here that the average velocity is the slope of the secant line. And the slope, well, formula for slope when we have 2 points here. By the way, this point is 2, 180. And this point here is 0, 0. So let's just find the slope. That'd be subtract the y's and subtract the x's. So the average velocity over these 2 hours was 90 kilometers per hour. I can see geometrically that s of t, this position function s of t, is continuous and differentiable on the closed interval. Well, it's continuous on the closed interval from 0 to 2, and differentiable on the open interval from 0 to 2. So the mean value theorem here applies. And in this particular case, because this is an application, when we connect the 2 endpoints, like we do for the example above, this actually means something. When we connect these 2 endpoints, this means that's the average velocity over the 2 hours. So therefore, because the mean value theorem applies, there must exist a c that is in the interval from 0 to 2 where the instantaneous velocity at a particular point is equal to 90 kilometers per hour. Which makes sense. If you go driving in your car for 2 hours, you travel 180 kilometers, okay? Your average velocity over those 2 hours is 90 kilometers per hour. There must have existed some point in that trip where your instantaneous velocity was also 90 kilometers per hour. At least one point. And so, and by the way, if instantaneous velocity at a certain point in time would be the slope of a tangent line, not the secant line. So it looks to be somewhere around here. And this is not a real function, but I'm doing this just to show you the geometric interpretation. It actually looks like there's a few points where the instantaneous velocity was the same as the average velocity. At this point here, this c looks somewhere around here, looks like it's going to be there. And also here. It might be multiple c's. But at least one time, the slope of a tangent line at this point had to be equal to the slope of the secant line, or in this case, average velocity. Okay. So that's about going to do it for this video. I appreciate you guys watching Bird Math. I hope you guys like my videos. I hope you think I'm pretty good at explaining this stuff. If you guys have any suggestions for future videos regarding any calculus, college algebra, multivariable calculus topics, I would love to hear them, and I'd love to make a video. So thanks for watching, and I'll see you again. Bye.